Hello students, welcome back to SapphireBlueChemspark. Let us start our today's session, the chapter Coordination Compounds from Inorganic Chemistry. So the last session we completed the introduction part and Werner theory of coordination compounds. Today let us begin with the definitions of some important terms used for coordination compounds. The first one, coordination compound and the coordination entity. The last class I said about coordination compounds are the special salt in which the central metal atom or the ion is surrounded by a fixed number of neutral molecules or group of atoms or ions. That is what said to be a coordination compound. So that coordination compound contains coordination entity. So the coordination compound is having coordination entity in which the central metal atom or the ion is surrounded by a fixed number of group of atoms or ions or neutral molecule, and it is always given in a square bracket. So a coordination compound that contains coordination entity. So this entity is made up of, see, the cobalt is the central metal atom or the ion, and the Cl3NH3 are the group of atoms or ions or molecules that donates a pair of electron to the central metal atom or ion, and which is always being enclosed in a square bracket. So this is what said to be coordination entity, and this coordination entity that may have a charges also. In this case I didn't mention the charge, it is just like taken as 0. So when this coordination entity bears a neutral, that means neither positive charge nor the negative charge, such coordination entities are said to be neutral complexes. Why it is neutral complexes? Because this complex is made up of a neutral molecule and a negatively charged ion. Neutral molecule is ammonia whose charge is 0, and the negative ion is chloride. Each chloride has -1 charge. 3 into -1 -3. In this case, the cobalt is existing in +3 state. So the net charge of +3 and -3, that makes the 0 for the entire coordination entity. So such entities are said to be neutral complexes. Suppose if these complexes having a positive charge are said to be cationic complexes, or else if the entity carrying the negative charge are said to be anionic complexes. So the cationic and anionic or even the neutral complexes is as a result of the charge carried by the fixed number of group of atoms or ions or molecules. Usually they are referred as donor groups or donor atoms. So they are capable of donating a pair of electron to which the central metal ion is bound. So here, if at all the donor groups are neutral, they will bear the neutral charge 0, or if at all the group of atoms or ions bearing a positive charge or the negative charge, as a result of it we can calculate the charge of the complex. In this case, cationic complex I have written. You may find the coordination entity is carrying 2+ or the 3+. When it has the 2+ or 3+, if at all the complexes are made up of neutral molecules, neutral having a 0 charge. So 6 times of water, 6 into 0, 0. 6 types of ammonia, 6 into 0, 0. So in such cases, the entities will have the charge only the oxidation number of the metal carrying. For example, in this case nickel, it is in +2 state, and hence the overall charge of the entity becomes 2+. Here iron carries 3+ state, so the entire entity that bears the charge of 3+. So such complexes are said to be cationic complexes. If at all anionic complexes where the complexes are made up of negative charges, then the donor groups must have a negative charge. So in this case, chloride, each chloride having -1 charge, totally I have 4 chloride ion, so there would be -4. Copper, whose oxidation state is +2, -4 +2, the net charge is 2-. Similarly, here cyanide, it has -1 charge, totally I have 6 cyanide ions. So 6 into -1 -6, where chromium that carries the +3 state that can be given in the Roman numerical. So -6 +3, the net charge is 3-. So coordination entity is nothing but the square bracket that encloses central metal atom or the ion and its fixed number of ions or molecules, that means the donor atoms. So as a result of the difference in charges of the donor group and the central metal ion, they can have a charge or even they could be a neutral complexes. The second one is, what do you mean by central metal atom or ion? These central metal atom or ions are usually from transition element because those only have vacant n-1 d orbital and ns orbital. So here these central metal atom or ion are capable of accepting the electron donated by such donor groups. So a central metal atom or ion, it is that the central of the one, the complexes to about which only the rest of the groups or ions are surrounding. That's why the atom or the ion is usually represented as central metal atom. So in this case, here it is being accepting the electron. Electron acceptors are referred as Lewis acid. So this central metal atom or ion that can also be termed as Lewis acid. So here we may find the central metal atom or the ion is actually bonded with its donor atom through coordinate covalent bond. The arrowhead, it is meant for the direction of donating electron from which group to which one. So cyanide, all the 6 cyanide that donates its pair of electron to the central ion. So this is what the direction from which the electron is being given to the other. Such bonds are said to be coordinate covalent bond. And in this we may find the fixed number of cyanide ion, that is equal to how many? 6. And the central metal ion in which the oxidation state is 2. So both of them are enclosed in a square bracket, and the other, the group which is present outside the square bracket is the simple ion. The next one, coordination sphere. Once again, the central metal atom or ion and its donor groups, which are always enclosed in a square bracket, is said to be coordination sphere. And this coordination sphere is actually a non-ionizable sphere, because the last class we discussed about the Werner theory, the 2 spheres, ionizable and non-ionizable. So in this coordination sphere is the central metal ion is surrounded by the fixed number of donor groups, and hence the metal ion is not free, we discussed. So that is what that makes the coordination sphere of the complex. So coordination sphere usually non-ionizable in nature. But at the same time, the groups are the counter ions which is present outside the complexes is ionizable one. So coordination sphere is non-ionizable, and the groups are the counterparts will always be ionizable part. The next one, what do you mean by coordination number? Coordination number is the fixed number of group of atoms or ions or neutral molecules that surrounds the central metal atom or ion is said to be coordination number. So every cases the coordination number may differ. So this is depending upon the number of vacant orbital provided by the central metal atom or the ion. If at all they provide 6 vacant orbital, then 6 groups of atoms or ions can donate the electron pair where the coordination number goes to 6. Or if at all the central metal atom or ion can have only 4 vacant orbital, then only 4 groups of atoms or ions or molecules can donate its electron pair where the coordination number becomes 4. So such a way the coordination number is nothing but the number of electron pair accepted by the central metal atom or ion, and it is always fixed in number for a given complex. So let us consider in these cases chromium, hexa aqua chromium 3 plus. I said hexa, this is what the coordination number of chromium. And here tetraamine nickel 2 plus ion, where the tetra 4 is the coordination number of the nickel. Similarly in COF6 3 minus, here once again the coordination number is 6 for cobalt, and that of trioxalato cobaltate 3 minus. In this case, this oxalate ion is capable of donating 2 pairs of electron. Here these are able to donate only one single pair of electron. That's why we said just having 6, 4 or 6. But in this case the donor group is 3 times present, but each group is capable of donating 2 pairs of electron. So we have to multiply 3 into 2, that is equal to 6. Therefore, once again the coordination number of cobalt is 6, not supposed to be taken as 3. So here the donor groups have a tendency to donate a single pair of electron or more than one single pair of electron, and electron donor groups actually referred as ligands. Ligands are the group of atoms or ions or the neutral molecules that surround the central metal ion by donating one or more unshared pair of electron to make a dative bond with the central metal atom or the ion, and hence these are referred as Lewis bases. Lewis bases are electron donors. So ligands are simply donors. What they can donate? They can donate a pair of electron. They have to donate a pair of electron to the central metal ion. Okay, so in this case I can represent the cobalt. It has the 6 cyanide group. So the formula for this is COCN6. This is what represented in the coordination entity. So central metal ion is surrounded by 6 cyanide group. That is what given. So here the donor groups are CN, in which the carbon is the donating group atom. So out of cyanide, carbon is capable of donating its electron to the cobalt, but not the nitrogen. So in the donor group we may find the donor group as well as the donor site. So donor site which will bear a negative charge or which will have a pair of electron that alone can donate its electron to the central metal ion, that is said to be, we can have a dative bond is formed between the ligand and the metal ion, through which the donor site is capable of giving the electron pair from the donor molecule or the donor ions. So in the ligand, if at all it is composed of more than one atoms, then only one of the atom is capable of donating its electron. Suppose if I have the compound of the type COCl6 3 minus. In this I have only chloride. So chloride alone can give electron to cobalt. But in the previous case cyanide is there. I have carbon as well as nitrogen. So there might be a question, which of the atom can donate its electron? So here I said carbon is donating the electron to the central metal ion, and hence the carbon is the donor site of the donor molecule cyanide. And depending upon the number of donor atom or the capable of donating the electrons, it is said to be density of the ligands. If at all capable of donating only one pair of electron, those are said to be unidentate ligands. Some example of unidentate ligands are halide, hydroxide, cyanide, nitrite, or if we can continue, so many number of ligands are there, that and all will be discussed in nomenclature. So let us find some of the example for the density of the donor group. So unidentates are the one capable of donating only one pair of electron, that may be a charged one or even the neutral molecule like this ammonia. Then if at all the donor group has more than one site to donate the electron pair, such groups are said to be didentate ligands. In this case we may find the oxalate as well as ethane 1,2 diamine. Here two of the atoms or two of the groups capable of donating the electron pair to the central metal ion. Similarly, we can find a tri or terdentate, tetradentate, hexadentate and all. So when number of the donating site increases, then the structure or the stability of the complexes also be increased. Besides comparing the unidentate ligand, the hexadentate ligand that make a highly stable complexes compared to the complexes formed by unidentate ligand. This is why, because of the chelating effect of the ligand. Chelates, those are all the 6 groups will surround the central metal ion such a way that makes a greater stability to the complex. That's why such a type of ligands are said to be chelates, as well as the ligands are called chelating ligand, and the effect is known as chelation. Depends upon the different pronunciation, we can say it is either chelating or even chelation. The next one, we have, besides the density of the ligands, we have one more kind of ligands known as ambidentate ligand. The ambidentate ligands, it is only one kind of ligand, that is the unidentate ligand, but it has more than one donating site. That's such ligands are said to be ambidentate ligands. So unidentate ligands have more than one donor atom through which they can bind with the central metal ion. Such ligands are referred as ambidentate ligands. So we can have NO2 minus. NO2 minus is the nitro ligand, in which when nitrogen is the donor site, then we will make the nitrogen that makes dative bond with the metal, or else it's ambident. We have nitrogen as well as oxygen. No, in one case nitrogen is donating and the other case oxygen is donating its electron pair. So here we are finding the metal is bonded with through the oxygen atom of NO2 group. Similarly, cyanide. Cyanide, it has that isocyanide structure also. In this case, carbon is capable of donating its electron pair to the metal, or else if nitrogen is donating, then it is given nitrogen is making the dative bond with the central metal atom. So ambidentate ligands are the unidentate ligand in which they can have more than one donor atoms through which they can make a dative bond with the central metal ion. And what are the types of ligands? Here we discussed about the density of the ligand as well as the ambidentate ligands. The ligands are of either positively charged, negatively charged or even neutral molecules. So we can classify, depends on the charge of the ligand. They are classified as neutral molecules, positive ligands and negative ligands. Neutral molecules, they will have a lone pair of electron and they don't have any charges and all. So these are molecules only. For example, water, ammonia, nitric oxide, carbon monoxide, these and all behaves as neutral molecules. Positive ligands, nitronium ion, this is nitrosonium ion. So these are having the positive charge that can able to donate its electron pair to the central metal ion. Though they have the positive charge, the other atom will have a pair of electron that will be given to the central metal ion. The next one, negative ligands. Negative ligands, they may have a either a single negative charge or even a di-negative charge like SO4 2-. So these and all having the negative charges, such ligands are said to be negative ligands. The next one is coordination polyhedra. Polyhedra is nothing but the geometry of the coordination entity alone. In a coordination compound, we have the two spheres, ionizable and non-ionizable. The non-ionizable spheres can alone give rise to such polyhedra. So in this case, the group of atoms or ions that donates the shared pair of electron to the central metal ion that finds a definite spatial arrangement in a given space about the central metal atom or ion. So that definite orientation or the spatial arrangement of the group of atoms or ions, that means the donors, that gives rise to the different polyhedra or the geometry for the complexes. So the polyhedra is totally depending upon the fixed number of the central metal atom or ion, that is the coordination number. If the coordination number is 2, then it has only the linear geometry. Suppose if the coordination number is 4, that may have either square planar or tetrahedral geometry. Or if the coordination number is 5, it may have trigonal bipyramidal geometry or square pyramidal. If the coordination number 6, it will be a octahedral geometry. So some of the geometries are just depicted. You can find this is the tetrahedral geometry. And the other one, it has the square planar geometry. This is a square planar, and here it is a square pyramidal geometry. It is a square pyramidal, and in this case it is trigonal bipyramidal geometry. This is octahedral. So these geometries are just given. Not only the coordination number, we have to find out their hybridization also. Based on hybridization as well as the coordination number, the non-ionizable part of the coordination compound may take either of the geometry. The next one, oxidation number or oxidation state of the central metal atom or the ion in a given complex. Oxidation number of the central metal ion that can be calculated just like how we will calculate for a given compound. In a compound, we used to say the sum of oxidation state of the different elements or the atoms present in a compound is always equal to 0. If at all the compound is a neutral, or if it is ionic, then the sum of the oxidation state will always be equal to the charge carried by the ion. Such a way only we are going to find out the oxidation state of central metal ion. But we have to define the term, what is the oxidation state of central metal ion. So what we know, the metal ion, once it is formed, that provides the vacant orbital, to which the donor group donates its unshared pair of electron to make a bond. So in that case, when you remove all the donor groups groups from the complex, then the metal ion will bear its own residual charge alone. That residual charge is termed as oxidation state of the central metal ion. So let us find some examples of calculation of oxidation state of central metal ion. The first case, I have taken hexafluoridocobaltate 3-. It is an anionic complex because the charge of the complex is 3-. I should find what is the oxidation state of cobalt. So I can write separately here. The unknown element is taken as X. How many fluoride I have? 6 times. So 6. What is the charge of the fluoride? Mononegative charge, uninegative charge. So 6 into -1. What is the charge carried by the complex? 3-. So what I said? The sum of oxidation state of the individual is equal to the charge carried by the ion. So X plus 6 into -1 equal to -3, or X equal to -3 plus 6, so that gives +3. Therefore, the residual charge or the oxidation state of cobalt in cobalt hexafluoridocobaltate 3 is 3. Or else you can go here. In this, the charge carried by the complex is 3+, so it is a cationic complex. In this cationic complex, the ammonia is a neutral molecule. It has no charge, but it can have a shared pair. It can have a lone pair of electron. So 6 ammonia molecule can donate 6 lone pairs of electron. But being the neutral have no charge, and hence this is the unknown X plus 6 into 0 equal to the charge carried by the complex 3+. 6 into 0, 0. Therefore, X equal to 3+. So, in this case, the cobalt that carries the +3 oxidation state. Here, we have a negative ligand as well as a neutral ligand. The fluorides as well as chlorides, all of them are negative, anionic. So, chloride it has -1 and the neutral ligand that has 0. So, X plus 3 into -1 plus 3 into 0 equal to the sum of the oxidation state of the complex. It has no positive or negative. So, it is taken equal to 0. So, this complex is a neutral complex. The first two cationic, anionic we had because of the charges of 3-, 3+, but in this case the complex has no charge at all, and hence it is said to be a neutral. For the neutral, the sum of oxidation state is taken as equal to 0. Therefore, X plus 3 minus 1 plus 3 into 0. Here it is called X minus 3 equal to 0 or X equal to plus 3. So, here also cobalt find its oxidation state of 3. And in coordination compounds, the oxidation state must be represented in Roman numerical. In all these cases, I have taken a ligand can give a pair of electron alone. Suppose if the complex it has a didentate ligand, that means if at all able to donate a 2 pairs of electron, where you have to count the number with twice the time. That's it. For example, I can write COEN twice Cl2 whose charge is plus. CO I am going to find out plus 2 into En, that is ethane 1,2 diamine, that is also once again a neutral. So, I can take 2 into 0 plus chloride 2 into -1 equal to plus. So, I can write X minus 2 equal to plus 1 or X equal to plus 1 plus 2, that is equal to once again what? Plus 3. So, here the oxidation state of cobalt is 3. This is the way how to find out the oxidation state of central metal ion in the given complexes. The next one is effective atomic number. Effective atomic number is shortly given as EAN. It is abbreviated as EAN. What is the usefulness of effective atomic number? When we calculate the effective atomic number of the given complex, we can able to predict the stability of the complex. If the EAN value that takes the atomic number of the following or the next inert gas, then the complex is said to be more stable. So this is calculated by following this formula. So EAN, that is equal to Z minus oxidation number plus 2 into coordination number. This Z is the atomic number of central metal ion. So this is atomic number of central metal ion or an atom. And this ON is the oxidation state of central metal ion. CN, this is the coordination number of the central metal ion. So in this case we are going to find Z minus oxidation number plus twice the number of coordination number. So that can be applied for the given complex FeCN6 4-, in which the atomic number of ion is 26. So this is what Z minus its oxidation number is 2, because how many ion I have cyanide? Cn 6 times, this is minus 1, 6 into minus 1 minus 6, so I can write x minus 6 equal to minus 4 or x equal to minus 4 plus 6, that is equal to plus 2. Therefore, ion whose oxidation state is 2, that's why 26 minus 2 plus. What is the coordination number of ion? 6. Therefore, it is 2 into 6, twice the time of coordination number. Now solve it. 2 into 6, 12. 12 minus 2, 10. 10 plus 26, that is equal to 36. 36 is the atomic number of krypton. So, as this EAN value takes the atomic number of the inert gas, then the complex is said to be more stable. The next one, homoleptic and heteroleptic complexes. This is nothing but the formation of the entity, if at all, by only one kind of ligand, it is said to be homoleptic. If the entity has more than one kind of ligand, that is said to be heteroleptic complexes. See that the coordination entity of the complex is made up of only one kind of donor groups or the ligands, is said to be homoleptic complexes. In this example, this complex is made up of only the cyanide ligand and it is made up of only the ammonia molecules. Similarly, if the coordination entity of the complex is made up of more than one kind of ligands, then such complexes are said to be heteroleptic complexes. So in this case, the first one, it is made up of ethane 1,2 diamine and chlorine. The next one, it has ammonia molecule as well as chloride ion. Here it has water molecule, nitrosyl group as well as chloride ion. So such complexes are said to be heteroleptic complexes. So these are the different terms which are used to describe about the every part of the coordination compounds. So coordination compound is made up of coordination entity, which is the non-ionizable sphere, and it has the counterpart of ionizable sphere. This non-ionizable sphere depends on its coordination number. It can give rise to the different spatial arrangement. As a result of that, we will get a polyhedra. And based on the charges of the donor group, we can able to identify the oxidation state of the central metal ion. And coordination number, it is a fixed number of the central metal ion. And depends on the coordination number only, the different geometry will be formed. And we have EAN, effective atomic number. The effective atomic number that predicts that stability of the complexes. And we also discussed about the types of complexes. Besides cationic, anionic and neutral, we have one more type of classification of complexes, homoleptic and heteroleptic. So based on the different definitions what we discussed so far, we can illustrate a complex. Here CONH3 6Cl3 is taken, that is hexaamine cobalt 3 chloride. So in this case, this is what the counterpart is said to be ionizable, and the entire coordination entity is said to be non-ionizable. And the CO is the central metal ion of the complex, and the 3, the Roman numerical, that represents the oxidation state of the cobalt, and the group of fixed number of molecule bind with the cobalt is said to be ligands. And how many groups are attached with the cobalt? 6. So that is said to be the coordination number of the central metal ion, and the ligand and the central metal ion, which are enclosed in a square bracket, is said to be coordination sphere. This is how we are describing the different terms which are present in a given complex. That's all. Okay students, let us close our today's session, and we will continue the same chapter in our following sessions. Until then, bye bye.